Hello everyone, today we are going to discuss about radioactivity as a phenomenon in physics. So, what is radioactivity? Uh, what is the phenomenon radioactivity? So, when we talk about radioactivity, we generally discuss about the nuclear phenomenon. It's a nuclear phenomenon. It's a nuclear phenomenon of of releasing alpha particles, beta particles, or gamma rays from nucleus. Now, notice that I have used word or here, and it means that at a at a time period or at a timestamp, it is allowable for only one of these particles or one of these things to come out of the nucleus. So it means if we have an alpha particle coming out of that nucleus in this moment, then until and unless that alpha particles come out of the nucleus, no other no other gamma ray or beta particle may come along with the alpha particle from the nucleus. It means this alpha particle release, beta particle release, and gamma ray release are the instances the instances of these release are mutually exclusive. You might use this word here, mutually exclusive. One event obstructs the other. So this is what the definition of radioactivity suggests. Now let's try to understand this definition a little better. So we have called that to be nuclear phenomenon because we know it's a atom. If it's an atom, it's the nucleus of it, and inside this nucleus, the cause, the main cause of this radioactivity is proton neutron ratio imbalance. That means if either of proton or neutron are greater than each other, then that would cause the imbalance inside the nucleus, and that would result into releasing of these particles. Now, now let's understand what I mean by this PN imbalance. When we see nucleus of sodium, then we can see we have 11. It has an atomic number of 11, and it has 11 protons and 12 neutrons. So we can say neutron by proton ratio is greater than 1, but it's just equals to 11 point, so 12 divided by 11, that's just 1.09. Again, if we see the nucleus of calcium, then it has protons, it has 20 protons and 20 neutrons, so the neutron by proton ratio is 1. Similarly, if we see some heavier electrons, then for example, let's say gold nucleus, then it has neutrons of 118 and the proton number just of 79. So we can say that the neutron by proton ratio is 1.49, which is very larger than 1. But it doesn't quite mean that gold is a radioactive element. So what is that specific boundary or specific limit of neutron by proton ratio which would help us to confirm which of the element is radioactive? So if you ask that to me, I would say there is not quite value for the ratio of neutron by proton ratio for dictating uh, either this element is this nucleus is radioactive or not. But there is something what we call as a belt of stability that would define us, that would help us to find and define which of the nucleus is uh, radioactive or not. So for that, let's see that belt of stability. If you see this curve, now this belt of stability represents the neutron by proton ratio of all 118 elements discovered in the nature, and it suggests us that we have something called 1:1 ratio line, which is defined by this line here, and this dotted line shows the deviation from that neutron proton 1:1 line. And the electrons, sorry, the elements or the nucleus that are shown in this dotted line are actually radioactive in nature. Okay, so what we can say is, even though we don't have that kind of rigid number of ratio to define which one is radioactive, we have this line, and deviation of this line, the much more deviation there is, the much more radioactive the element might be. So this is how we define which one is radioactive and which one is not. Now, after understanding this, you should also understand what kind of radioactive decay would happen to what kind of particular cases. So let's discuss cases of decay. Okay, so when we have a nucleus with higher number of neutrons, then it need to transform the neutron to protons to stabilize the ratio. In that condition, what we get a beta minus decay. Similarly, when we have a nucleus with higher number of protons, then it needs to transform that proton to the neutron to stabilize the ratio. That's why at that condition we have beta plus decay. Similarly, when we have a large nucleus, it means we have large number of neutrons as well as protons. Then in that condition, the nucleus would tend to release a large chunk of it, so that the nucleus would be stabilized more faster, and that kind of ratio, and that sorry that kind of scenario would result into alpha decay. Similarly, when that nucleus has too much of energy, or it just goes it just has been undergone alpha decay or beta decay, and it has a lot of energy inside it, inside the nucleus. Then it need to release that energy, and in that condition, uh, gamma decay happens. Okay, so this is the overall scenario and overall scenarios where a different kind of uh, decay happens in radioactive in radioactivity. Now, let's understand, how does alpha or beta rays and gamma rays actually get out of that nucleus. Okay, so let's see this. So we have inside nucleus structure there, and we have something called potential well, and we have something called outside of nucleus. What does this figure mean? Now this figure wants to depict the nucleus and nuclear boundary. So you can think of this to be as, so this thing this thing is inside the nucleus, and even inside the nucleus we have two layers. First one is the internal layer, and second one is outer layer, and in between the internal and the external inner and outer layer, we have something called potential well. Okay, potential well, and this potential well is actually just a name or just a depiction of strong nuclear force. A strong nuclear force in between the proton and nucleus that would interact with the other particles that would try to go out of this nucleus. Okay, so let's suppose we have a nucleus, and inside nucleus we have alpha particle and beta particles. Actually, beta particles are uh, not produced uh, beforehand. They are just produced during that moment of decay. That's why we don't. Uh, let's not talk about beta for a moment. Let's just focus on alpha particle. So if you see alpha particle, now alpha particle is actually helium nucleus, which has this kind of electron configuration. Not the configuration, but kind of symbol. Now you need to know some fact here. Now the first fact you should know is that the alpha particle itself has an energy of 4 mega electron volt. Okay, you can calculate that by considering the fact that each electron has an energy of 1 mega electron volt. So 4 of the electrons would be have not sorry I don't think it was quite well. I just wanted to say that each of the electron has certain amount of value, and if you calculate that with that 2 or multiplied with that 2, you would get 4 mega electron volt. Similarly, this potential well is also has a height of 9 mega electron volt. So we can see there is a difference in between these alpha particle and mega electron and potential well. And now you must be wondering, how does this 4 mega electron volt alpha particle is able to overcome this potential barrier of 9 electron volt? And the answer to that is it doesn't. It doesn't quite uh, it doesn't quite overcome the boundary. Now you may argue that it now we and since we are talking about alpha decay, alpha release, alpha ray must have some way to get out of this nucleus. If it doesn't overcome this potential well, how does it comes out of this nucleus? And it is very interesting too, and it is very confusing, and it's very obvious of you to get confused in that. So let's understand what's going on here. So even if even if alpha particle doesn't have that much of energy to quite match or overcome this potential barrier, it has a high speed, and because of that, it can do some it can do collisions of order 10 to the power 21 times per second. So it has a frequency of 10 to the power 21. So it hits this boundary 10 to the power 21 times a second. So this means that alpha particle is trying very hard to get out of that potential world, but it doesn't had success yet. So one thing that you might understand, you might want to know before understanding this is every particle inside the nucleus has some probability of tunneling through this potential well, even if they doesn't have that much of energy. So if you take any kind of other element, for example, not only the helium nucleus, let's take a Gn nucleus. So not Gn nucleus, but let's take a sodium nucleus. Okay, so let's suppose a sodium nucleus would be uh, like this. So let's suppose a sodium nucleus wants to come out of this of this nucleus. Now it won't it would have some probability of tunneling through this, but the probability would be so negligible that that probability won't practically happen. But in case of alpha particle, the probability of tunneling through this potential barrier, even if it doesn't have that much of energy to overcome that barrier, is quite appreciable. Okay, it might happen. That's why alpha particle tunnels through this potential barrier of the nucleus, defined by strong nuclear force in between proton and nucleus, proton and neutrons. Okay, so this involves quantum tunneling. So this also answers the question that if the nucleus is so desperate to to be stable, then why doesn't it just release its all energy in at once by releasing a large nucleus? Why does it keep uh, keep throwing small alpha particles to us? And the answer to that is that the probability of throwing that out of this potential well is very negligible. We can't even say that to be a probability. We cannot say that to be a probable event. Okay, so so we don't take that much attention to that. We don't take much importance to that. That's why. That's why alpha particles are the biggest ones, or are the largest chunks that has that probability of getting out of this potential well. So the nucleus is smart. That's why it makes the chunks just as large as the alpha particles to throw them out of this nucleus to stable themselves. Quite genius, isn't it? So this is some inner details, insider details about what's going on in nucleus. Now you may wonder, okay, so alpha particle have that kind of probability, right? Then uh, why does the beta particle isn't a bigger one, or why just a nucleus, just single electron? Why isn't it two electrons? Why isn't the beta particle made up of two electrons? Because two electrons has some probability, right? Now the answer to that is you are not quite getting the concept here. Alpha particle is the helium nucleus. It doesn't mean that uh, this beta particle has to be something like that. Actually, the beta particles are produced instantaneously when there is some when there is higher number of either of electrons, either of neutrons or protons. That means these beta particles are produced instantaneously. And when I say instantaneously, this beta particles are also governed by weak weak nuclear force, weak electromagnetic force, rather than a strong nuclear force. So they become invisible to this potential well. So for the beta particle, there is no potential well at all. So that's why it become invisible to that potential well and can go without even tunneling, without even any effort. So this world of nucleus is quite biased. Okay, so this is how the alpha particle and beta particles are released by the nucleus. I think it was quite fascinating.